So welcome, I'm John Roese, the Global Chief Technology Officer and Chief AI Officer of Dell Technologies, and with me is Andrew Dzurak from Diraq. These are, maybe you've never met Andrew before, and you might not have even heard of Diraq, but as a really interesting technology becomes much more mainstream to us, quantum, we thought it'd be a great idea to have a conversation, share what we've been up to, and so welcome, Andrew. Why don't you give people a bit of a background on what you've been up to and what your company does?
Of course. Look, thanks, John. It's great to be here with Dell. Diraq is a company that's building quantum computers based on standard silicon technology. So quantum computing, as we're going to talk about, has amazing opportunities to expand high-performance computing and AI and go really where AI is reaching some of its limits. We're developing computers that are compact, very energy efficient, and can be integrated with the sort of infrastructure that Dell produces so brilliantly.
And it's interesting because years ago we concluded that this was going to be a team sport to get quantum into the real world. It wasn't just about the QPU or just about the CPU or just about the software. And so we've been working together on a bunch of stuff. So, why don't you share kind of the Dell Diraq collaboration that's been going on?
Absolutely. A little over a year ago, we started talking to some of the really good engineers at Dell who'd been looking at quantum computing. And we've been part of a large program run by the US government through DARPA called the Quantum Benchmarking Initiative, which is aiming to build what are called utility-scale quantum computers. These are quantum computers that show genuine commercial advantage well beyond the cost. Now, what we've been talking about for the past year with Dell is how to integrate Dell's classical compute systems with our quantum computer systems that we're developing at Diraq. And we've already kicked some goals just in the past few months.
Yeah, I think it's, this term, by the way, the term of the day for everybody in the future is hybrid classical quantum computing. And what we realized, most of us in the industry, was you were going to build a system that had multiple types of compute in it, because it turns out that the really complex problems in the world include multiple types of mathematics. And CPUs are good at some mathematics, GPUs are good at some mathematics. None of them are very good at the kind of mathematics that happen inside of a QPU. And so, the net result was we concluded the industry would have to build these systems that brought all of this type of compute together into some ability to process outcomes that would go after problems that we hadn't been able to solve before. What's your feeling on the progress of building hybrid classical quantum computers?
Well, come to your point, John, you're absolutely right that quantum computers are exquisitely good at solving certain classes of problems, but they're actually very, very bad at solving a lot of problems that are commonplace and solved by CPUs and many GPUs. So it's vital that we create hybrid systems with quantum computers working alongside high-performance AI and other CPUs and high amounts of memory storage. This all has to be integrated. The type of problems that quantum computers are going to be really good at are problems that are actually too difficult for AI. And a classic example is trying to describe the way nature works at the molecular level, right? So this is areas such as pharmaceutical design in medicine and many other areas where we have to actually describe the real inner workings of a molecular system. Now, for those sort of problems, there's a lot of compute that needs to be done classically, and AI can do a lot of that very well, as can CPUs. But there are certain problems that just become impossible. It could take the lifetime of the universe to calculate when we're looking at a really complex molecule. So you're going to have systems, and we're working with Dell on creating these integrated systems that call the classical AI and CPUs for a lot of the big number crunching. But then when there's a specific hard problem about describing a molecular system, then you call the quantum processing unit the QPUs. So that integration is something that we're focusing on at the moment with the Dell team.
Yeah. The fascinating thing is that's actually real. I mean, we have prototype systems, we have real hybrid classical quantum computers in the early stages. I think one of the most salient points you raised, which people, when they start to understand quantum, is they realize that there are lots of natural systems that we have effectively simulated in compute. We've converted nature into binary, and then we've run algorithms against the binary representation of nature. And I think you and I were talking about this when I was in Australia, and we've had this conversation that the big breakthrough is that we can now kind of skip that analog to digital conversion, and because quantum computers can actually work at that level where they're really dealing with kind of unadulterated natural representation of what's happening, they're actually just logically better and more aligned to those kinds of problems. But it sounds complex, but there's a whole bunch of problems that we couldn't even comprehend, so we had to abstract to apply compute to, that we no longer have to do that abstraction. I think that is super exciting and opens up just an incredible frontier.
That's right. I mean, the original idea of quantum computing goes back to a Nobel Prize winner, Richard Feynman, who was at Caltech and was talking about the future of computing some decades ago. This is like in the 80s. And he was asked, where can computing go in the future? And he said, well, you're going to get more and more bits on a chip, but there are certain problems that conventional computers just can't handle. And these sort of problems of describing molecules are those specific problems where quantum computers are naturally suited to describe the molecular world, because the molecular world is quantum mechanical. And so it's a natural fit.
Yeah. And beyond that, we've been experimenting with early quantum systems, annealers, and early simulated systems in our supply chain and other areas. And we discovered there's this whole other class of problems called optimization problems, which, go Google the traveling salesperson problem or the airport gate problem. As you have kind of an n-squared environment, classical computing kind of runs out of steam. It's very, very complex for those things to be processed. By the way, that's also the root of much of the advanced cryptography of the world. Assumes those things are hard. What that tells me is that not only is this good for nature-inspired algorithms, it's also potentially good for the broader world. It could transform logistics, supply chain, all things in which we have to predict the future over a large range of permutations. This kind of mathematics may actually be incredibly disruptive and powerful.
There's also another whole class of problems, problems that have got a lot of variables that become very difficult to handle in one calculation with conventional compute. Finance is an example. So finance, of course, as we know, the economy is an incredibly complex beast with so many variables, and trying to do things like optimizing portfolios in financial management. Or, for example, if we're looking at things like fast trading, where where already AI is being used in order to enable trading to be done, at the sort of, microsecond and millisecond timescale. But you need high quality data to train those AI models. And this is another area where quantum computers are very well suited to doing that AI model training. So there are many different ways in which quantum computing and advanced AI overlap and integrate.
So what this is all great, and yet, we've been talking about quantum for a long time. Now the good news is there's some physical things we can touch and feel, and the DARPA project's very good about it accelerating. By the way, AI itself is accelerating quantum because it's making it easier and faster to do the work, to build the control systems. Where are we today on that journey? And then I'll give you the hardest question of the day, which is, when do we achieve kind of quantum utility or quantum supremacy, that we have things that actually make an impact?
Well, let me talk a little bit about explicitly what we're doing together with Dell. So we already have a couple of Dell servers working alongside our early stage silicon quantum computers at Diraq. And they're working in two different ways. There are two main ways in which high-performance computing and AI interface with quantum computing. One way is that they actually make quantum computers work better. So, for example, quantum systems are very prone to errors. So you have to do a thing called quantum error correction. That's very challenging. That is where advanced AI systems can help to optimize the error correction and the sequencing of the calculations. So we're already using a Dell server to interface with our quantum system at Diraq. The other way is, once you've kind of got this quantum computer, then you have to interface it with the standard classical computing, the sort of stuff I was talking about earlier. And so that's another way in which we're working with Dell. So we already have our early stage Diraq, small quantum processing units interfacing with Dell server racks. But looking forward to when we're really going to start to see this out into the market and making a change for customers, we're looking at a product as early as 2029 that will be beyond anything that can be done with conventional computing at the moment. So we're looking at a system with many, many thousands of physical qubits, over 100,000 physical qubits, and approaching 1,000 what are called error-protected logical qubits. Now that is a very, very powerful computer. And again, that needs to be integrated with advanced classical compute of the type that Dell is developing. So we're looking at systems before the end of the decade that are really going to be game-changing and are going to be very, very important, to high-performance compute customers all around the world.
Yeah, I get excited when I hear about the progress, because to tell you a story, about 10 years ago, I started our quantum work at the company, and we went out and talked to every quantum startup and researcher we could find. And then we came back and distilled what we thought was necessary for quantum to become real. And there were 3 things. We said we need to agree on what a quantum computer is. And today we have about 5 modalities. Most of them are all viable. There's going to be a debate about, you have a semiconductor focus, which I think is a very good thing. That's a way to get to scale. Some people aren't doing it that way, but the bottom line is we kind of know how to build one of these things. The second is we have to make it work in the real world, meaning we have to make, it can't be a qubit at any cost. It has to be qubits that actually have a bounded cost and actually are scalable and are big enough to do interesting things. And funny enough, the third thing we identified was these systems have to interface with the rest of the IT ecosystem, because in isolation they aren't very useful. And so that was software problems, interface problems, control problems. And we wrote that down 10 years ago and have been watching the progression. And what you just described is progress on all 3 of those and an end state. So I actually think, we're not decades away from this. We are actually much closer than we think. And and by the way, the algorithms keep getting better. So the demands of the quantum system are actually lower than they've ever been. No one can say when, but we're not that far away. And the kind of things we can do from it are fascinating.
John, I'd like to pick up on a point you made about the cost of the compute, because as Dell's well aware, you guys are all about trying to deliver the most computing power for the most cost-effective price, right? And also trying to drive down those energy costs, which also feed into price. You mentioned that our technology is based on semiconductors. It's based on the best semiconductor, silicon, of course. What our company developed originally in a research team a decade ago was a way to turn standard silicon transistors into quantum bits, okay? So that means that we can make quantum processor chips, QPUs, on the same chip, the same sort of size die, using the same manufacturing as is used to make all the chips in your servers, in our phones, and in laptops. And the crucial thing about that is that drives the cost of the system down. It makes it compact and low energy in terms of the amount of energy usage required. So in the size similar to the size of a rack in a typical Dell server, we're able to make an entire quantum processing unit. And we have calculated that we can do this at an effective cost of less than $1 per qubit, which really is the crucial thing that DARPA has been looking at. So DARPA defined a term, utility scale, as I mentioned before, when the commercial value outstrips the cost. And to do that, you've got to drive the cost down. So another factor about the integration is you want the system to actually fit inside a standard data center in an AI factory. And our systems, Diraq systems, are designed to be compact, to be slimline, to just fit inside a data center and integrate with low latency. This is another crucial thing. We were talking about the need for useful commercial algorithms are going to have a lot of classical compute and they're going to have quantum compute. And you want to be able to share that data quickly, low latency. Our quantum computers are very, very fast, and so we need information coming back very quickly. And so this tight integration in a standard data center environment at an affordable cost is just going to be crucial for the future.
We have a core principle, you've heard Michael say it, is we like democratizing technology. If only 3 people in the world can have a quantum computer, that's not what we're shooting for. We're shooting for the world being able to take advantage of it. And scale, size, cost, all of those things matter. We weren't, as an industry, necessarily obsessing about that 5 years ago. Today, we're getting closer to real production systems, and it's great to see the focus on it's not a qubit at any cost. It's qubits that can be democratized around the world, and we can actually solve problems at scale. So,
well, John, your CTO, you're always looking over the horizon. I'm interested, if you looked back maybe 5, certainly 10 years, and you were looking at AI, could you have conceived about the number of AI systems that are out there, the number of GPUs that are being used? My personal view is that quantum computing could well go in that same way, where we need thousands of quantum computing systems integrated with AI factories. I mean, what's your view? How hard to see the future? Or?
No. In fact, I am on the record telling people that as exciting as ChatGPT was, and as disruptive as that was, the day that we have viable, cost-effective, at-scale quantum systems, it's a bigger deal. It changes everything. It will open up mathematics that we've never been able to do, but even we're seeing this affinity to AI, where whatever the state of the art of AI is that day, dimensions of it are suddenly going to become orders of magnitude faster, cheaper, and better. And so, you guys benefit. The bigger the AI world is, by the time we have these technologies, the bigger that amplification effect is. I'm very much on the record of telling people don't think we're done. ChatGPT, generative AI was a big deal. Quantum is potentially a bigger deal because it will build on the shoulders of giants. It will build on where we are in this very modern automated world that's being formed right now.
And the thing about quantum compute, when integrated with classical compute, with Dell's technology, is we'll be able to control the natural world in a way that was only ever dreamed of. We're talking about the ability to custom design molecules that could be used in the chemical industry, in the pharmaceutical industry. We could be developing materials that make, planes fly much lighter but stronger, with far lower energy consumption. So the prospects for the ways that we can improve the life of humanity is phenomenal, and it's just an incredibly exciting time, and not very far away.
No, exactly. Well, thank you for the partnership. It's been a great interaction between our teams, but more importantly, we're working with governments, and we're really focusing on something that matters, and we're accelerating. So, any closing comments, any advice you want to give the people who knew nothing about quantum before we started to talk, but what they should think about next?
I think that they should think about how much, just in the past 1 or 2 years, the whole perspective of the world has changed because of what we've seen with AI and the developments. And our view is that they can see those same levels of change when quantum computing comes online in just a few years, right at the turn of the decade.
Yeah. So if you were hoping for a boring, uneventful industry, we cannot deliver that to you. So great. Andrew, thanks very much. Love the partnership. I appreciate you being here.
Been a pleasure, John.
Absolutely.
Thanks,
great.
man. Really enjoyed the discussion.
Thank you.
Thank you.